Images and bit depth. Computers work in binary, storing noughts and ones, whole numbers, otherwise known as integers. So the simplest image is a 1-bit image, 1 bit of information per pixel. The value stored is 0 for black and 1 for white. Here we have an excellent example. Next up in complexity we have an 8-bit image with 1 channel. This gives us in decimal values 256 grayscale values, which can give a very sophisticated but simple image. Let us briefly look at how this data is stored digitally. Our computer is storing binary information, 8 bits per pixel, either 8 zeros or 8 ones, and these 8 bits of information are mapped to corresponding decimal values, which give us 2 to the power of 8 options. 256 different shades of colour can be stored for that 1 pixel. These 8 bits take up 1 byte of storage. Okay, now let's look at this 10-bit image. Now with each extra bit of information that we add to our channel, we get a to the power of increase. So 2 to the power of 10 gives us our 10-bit channel with 1024 available colours. And this increases so on. So 2 to the power of 16 gives us our 16-bit channel with 65,500. And then 2 to the power of 32, our 32-bit channel, gives us 4,000 million different shades of colour, which should be enough. Now let's look at our 3-colour image in a bit more detail. This example has an alpha as well. So each channel has 8 bits of information per pixel. So we have 4 channels, which gives a total of 32 bits per pixel. Now let's look at the colour first of all, red, green and blue. Our resulting dark blue colour is a mixture of red, green and blue. For our red channel, we can read along the binary numbers and then map them up to their decimal equivalents, add up the integers, and in the red we get 46 hexadecimal value. Incidentally, the hex values are also available. And we do this, we read along 0101, add up the integers, and we come up with this value. And you should recognize these figures in Photoshop, these 0 to 255, giving us 256 different levels of color per channel, and combined together they give us 16.7 million colors per pixel, which sounds like a lot. And incidentally, in this example we have a solid alpha, so it has a 1 for every channel, a solid white alpha. Our previous example was 32 bits per pixel with the alpha. This example has no alpha, so it's a 24 bits per pixel, 8 bits per channel image, 3 8s, 24. Now it's worth having a look at these separate channels. We can see in the first one, the red, the ESC of escape on the bottle is got in white, it's got a high value, as does the top section where you unscrew the bottle. Now in the green channel, again the ESC has high values because the ESC is in white, so it's got high values in the red, the green and the blue. But we can see how the top of the bottle is low because there is not much green in red. If we look at the blue channel, you can see the ESC is relatively high, but nowhere near as high as the part of this crazy blue sphere, which is extremely intense blue. And then, as we can see, a low amount in the top of the bottle as we would unscrew it. And then if we look at them all combined, we can see, yes, that sphere at the bottom has got a very high blue. The ESC of escape is relatively high near white, and the top of the bottle being very red, as shown in the first red channel. Working in floating point. Whereas we discussed 8-bit per channels giving 256 different values as a starting point. Now the equivalent in float would be a 0 to 1 range, but you'll be working to at least 5 decimal points, which gives you much greater accuracy. So if you imagine if there was a value in between, if there was like a value at 100.5 in an 8-bit scale, then that would get either rounded up or down. Now if you were doing a number of calculations through a whole compositing process, maybe even tens or even hundreds, you would start to get errors in rounding up or rounding down. Now a 16-bit integer, still with 65,500 odd, you still have these problems, whereas in float, with your decimal points, you can just do almost limitless amounts of calculations and not degrade your image as you go through the compositing and 3D process. Floating point. Working with one 8-bit channel gives us 256 different levels of colour to work with. 0 being black as visible on the monitor and 256 being white as visible on the monitor, and there are no values stored above and beyond those. The advantage of floating point is that it allows us to store a much wider range of values. Also we can use numbers above 1 and below 0. This means that when you see a floating point image, typically it will have information stored in the blacks and whites that is not visible on the monitor immediately, but it can be used in calculations, and it can be seen by altering the lookup that we are using to look at the image. We looked at bits and bytes and storage, and we should have an idea that computers love these 2 to the power of numbers. They're very efficient for storing and using. So our texture files follow this format: 2 to the power of 8, 2 to the power of 9. These give us these 512 by 512, 1024 by 1024 maps, all these square formats, and these are often referred to as 1K maps or 2K maps, and these are used not only for our texture files but also for shadow maps and other temporary maps used in rendering. And if by chance we made a texture map which was 1024 by 1050 pixels, it would use as much RAM as one that was 2048 by 2048. So you can see immediately the efficiency gained by us following these conventions. Resolution of film plates. Okay, film can get scanned at 4K or 8K. If it was scanned at 4, you would get a plate 4096 pixels wide by 3112 high, otherwise known as a 4K plate. I mentioned at one time that a more usable size is 2K, 2048 wide by 1556. And don't forget that all of these dimensions are full aperture. There's no letterbox put on these.